Today's lecture are on my webpage, and today's will be posted. I'll try to post them every day. If you, it's linked from the conference webpage, from Balazs's page. So, okay. So, I'd like to continue with our study of this space Ben-Zvi. This moduli space of G bundles on a Riemann surface, and we study some of its features. So far what we've seen is two spaces that map onto it. First of all, there's the cotangent bundle of Ben-Zvi of X, and this we identified with the space of Higgs bundles on X. So these are, so if here we have bundle P, and here we have P and eta, where eta is adjoint valued or endomorphism valued one form. And on the other hand, we have the space connections G X. And so this is the space of P and nabla. And nabla is a flat connection on G, on the G bundle P. So there are several things to say about this picture. First of all, that, well, connections on X are not supported everywhere. Not every bundle admits a connection. Well, we saw that even in the rank 1 case. Only degree 0 bundles admitted connection. But wherever it's supported, the difference between any two connections is a Higgs field. So this is an affine bundle modeled on this vector bundle, at least wherever it's supported.
When you say connection, you mean flat connection?
Well, right. So now what do I mean by connection? So by a connection, I mean I have a holomorphic principal bundle, and I have a holomorphic connection. So nabla is a holomorphic connection, or algebraic, if you'd like, connection on this principal bundle. Now, one point to make is that since our Riemann surface X is a Riemann surface, there's no room for the curvature to go. So if you look at the curvature of a holomorphic connection, there are no two forms on the holomorphic two forms for this. So this curvature is automatically 0. So nabla is automatically flat. So holomorphic connections in one dimension are automatically flat. So this is a very useful point, is that the space con G, so on the one hand, we identified it with these one forms. Well, the difference was given by these holomorphic one forms, and if you like, they're closed. So you have this space of flat connections, and that tells us that we have another way of thinking about this space. So the space of flat, so now I'm going to think of this as the space of flat connections. Equivalently, I can think any flat connection, I can give a holomorphic structure. This space can be identified with the space of, well, we can give it different names. Maybe call it the space of G local systems on X, which I'm going to think of as monodromy maps. So to any flat connection, I can assign its monodromy representation, which is a map from pi 1 of my Riemann surface, some base point, to G. So for every loop in my Riemann surface, I look at the monodromy of the connection around that loop, and I get a homomorphism from pi 1 from X to G. And I get these up to conjugacy. But so I have an isomorphism like this. The reason I don't want to emphasize this too much is that this isomorphism, this is a complex analytic isomorphism, but it's not algebraic. So both sides of this are algebraic varieties. This was defined by algebraic families of connections on algebraic bundles. And this is given by a bunch of equations, explicitly just given by generators in G and the equations of the fundamental group. But those two algebraic structures don't agree, because assigning to a connection its monodromy is a non-algebraic thing. It's a kind of exponentiation. So complex analytically, this space has this property. And you'll notice that this complex analytically, this right-hand side, this is independent of the complex structure on X. As a complex manifold, this thing does not depend on the complex structure of X. It's just given by a bunch of copies of G with some equations. So the equation, it only depends on the fundamental group of X. While this side definitely does depend on the complex structure. Okay, so so this is the kind of picture we have. I would like to mention also there's probably a more familiar version of this picture, which is worked out by Hitchin for SU2 and Corlett-Simpson in general, which is this non-abelian Hodge theory picture. So I only want to kind of mention it very briefly, and we'll return to this on Friday, because this appears kind of was going to appear essentially in the topological field theory story. But one thing to say, so maybe before I even say that, like we said in the abelian case, if we have an affine bundle, modeled on a vector bundle, there's a deformation from this to this. So I could take this affine bundle and kind of rescale the affine structure till I get the vector bundle. So I could really think of this either as an affine bundle, or I can think of this as some kind of deformation. In this non-abelian Hodge theory picture, we have a different relation. So so the claim is that there's a good approximation to a large big piece, which is the kind of the nice locus, and formally this is what's known as a semi-stable locus of this space of Higgs bundles. This is the moduli space, which is I'll call MH, the Hitchin moduli space. And this is the moduli space of semi-stable Higgs bundles. So here, this is an honest algebraic variety, not a stack, and it kind of looks like an open piece of the Higgs space, except that you've collapsed some pieces a little further. So it's not exactly an open piece, but it's something like an approximation to a big open piece of this space. But this is a nice algebraic variety. In fact, so this is space of solutions of Hitchin's equations on the Riemann surface. And so I'll write these down on Friday. But this space has a lot of beautiful properties. In particular, it's a hyperkähler manifold. So it's a hyperkähler manifold, and so which means in particular that it has a P1, which is span of I, J, K worth of Kähler structure. Means it has P1s of Kähler structures. And I want what is the relation between this picture and what I'm drawing and this algebraic picture. So what does it mean? How do we think of this hyperkähler manifold? It means we have the same underlying smooth manifold, but we can think of it as a complex manifold in different ways. So we have a different complex manifold. In fact, we don't have a whole P1's worth of different complex manifolds. It turns out that as a complex manifold, there are really only three things. You have the complex structure I, its complex conjugate, and all the other ones are isomorphic. So there's a C-star action on this P1. Exchanging these complex structures. And so let me tell you what this space is in these complex structures. So this Hitchin space in the complex structure I is it's something that's, well, it's the moduli space of semi-stable Higgs pairs. So here, this is the complex structure that I get. So the I structure is the one that I gave before. So it's something like the cotangent bundle of the moduli space of semi-stable G bundles, but it's larger than that, has some extra stuff. But again, it's some kind of approximation for this space of Higgs bundles with its complex structure. And in the J complex structure, so the only other one I need to tell you, this is an approximation to this some kind of semi-stable locus in the space of connections. So in other words, the space of connections, there's some piece of it which is in fact diffeomorphic to some piece of the space of Higgs bundles. So rather than thinking of this picture as a deformation of these stacks, there are some pieces in here which are actually diffeomorphic And, or if you'd like, yeah, so they're actually diffeomorphic, and they're both different. And the two complex structures together define a hyperkähler structure on the Hitchin moduli space. OK, so I'll return to this picture on Friday in the topological field theory context. I just wanted to leave this sort of to connect to things many people here know well. Well, it's certainly a part of that space with a connection, but it's not exactly that. I mean, you need some conditions on your Higgs field. There's some stability conditions that I don't want to get into. The Higgs theory is not quite the right equivalent. I mean, there's a degree issue, but there's more than that. The support of the space of connections is given by a theorem of Weil. It says you need a bundle of all indecomposable pieces of degree 0. So there's some condition.
Aren't you getting the G-local systems complex structure when you look at the J complex structure?
I am getting the G-local systems complex structure, which is the same complex structure. So here I'm thinking of this as a hyperkähler manifold. This is the same holomorphic structure. It's not the same. I'm not thinking of it as an algebraic structure. So algebraically, this is different than how I want to think about it. But complex analytically, it's the same. OK, so all right. So now I like to leave this alone and for now, and I want to tell you a very beautiful story about this space, a very beautiful piece of structure on this space that's going to enable us to come up with some kind of Fourier theory. So we found out that, well, this space bound G of x, I haven't tell you what it looks like because it's complicated. And I'd like to give you some picture of what it looks like. Again, picture that's due to Hitchin, which is going to enable us to see parallels with the abelian story we had before. So this is the story of abelianization. So this is, in some sense, the most concrete picture of the moduli space of Higgs bundles we can come up with. And so what does abelianization, how does the abelianization story begin? So suppose I'm going to talk about this just for vector bundles. So just the GLN case. Maybe I'll make some comments later for other groups. So the first thing, how am I going to construct, how do you build a vector bundle on a Riemann surface? How are you going to construct a vector bundle on a Riemann surface? And the easiest way to build a vector bundle on a Riemann surface, if I have a Riemann surface x, a nice way to build it is to take another Riemann surface, y, which is an n-fold branched cover of x, and take a line bundle on y. So if I take a line bundle on a Riemann surface y, and I push it forward, I'm going to get a vector bundle on x. So here I have y maps by pi to x, and L is a line bundle in pick y.
You want, I mean, if the sheets come together, you have a problem.
I would.
That to be a covering space.
You would think so, but if you actually look at the local structure of the cover, that push forward is always going to be, always going to be a vector bundle.
The branching doesn't.
The branching doesn't affect it.
Still get a vector bundle?
Absolutely. So I'll comment on that in a second. So if I take a line bundle, the claim is I take its push forward to x, and let me call that v, is now a rank n vector bundle on x. So what's going on? So you're adding up. So what does push forward mean? So at a smooth point, where a non-branching point, this just means you take all the lines in the fiber and you add them up. You take the direct sum of all of those lines. And at a branch point, you'll find that you have one fewer point, but the push forward is a little smarter than that. It actually gets the first order jets of this. So it kind of compensates. So what happens is that and this is going to be the key points that, if you like, away from the branch locus, the fibers of V looks like a direct sum of the fibers of the line bundle. So your vector bundle is actually decomposed as a sum of lines, but that gives you a description away from the branch locus. And at the branch locus, you no longer get a decomposition into a direct sum of lines. So this is going to be very relevant. So what do we do now? So the Hitchin's discovery in this was there's a very close relation between the cotangent bundle of Ben-Zvi and this abelianization story. And so, first of all, we can say even first of all, you can think of this as a very good way to parameterize vector bundles. You take a nice y, and it turns out for a nice y, you're going to get an open piece of Bun n. You get a map that hits some open piece of Bun n. So you can think of this as a nice way to construct vector bundles. But something much more precise is true. So let me now think of what a Higgs bundle is. So suppose I take V and eta is a Higgs bundle. So this is in my T star of Ben-Zvi. Yes? Not for any fixed y. Right, so I mean you can, it depends what you mean by y. I mean you can, if you take y to be general enough, then you can cover. But so this will be hopefully clear from the picture I'll say. Okay, so what is a Higgs bundle? Let's just think what this is. Eta, what was eta? Eta was a matrix of one form. So I'll stop writing H naught. Eta was an endomorphism of V tensor one forms. But I'd like to reinterpret this. So instead of thinking of a matrix valued with one forms, I can equivalently think of it like you write a connection. We usually write a connection as a map from V to V tensor one forms, except that now this is a linear map, unlike a connection. So a Higgs field is the same as a linear map, linear over functions from V to V tensor one forms. But I'd rather dualize. So I'd rather think of this as a map from the tangent sheaf times V to V. So it's an action of vector fields, except again, it's a linear action. There's no Leibniz rule. Okay, but now this vector fields, because I'm on a Riemann surface, there's basically only one of these locally. I can just extend this action. Instead of saying I know how to act by one vector field, I can then compose this action with itself many times. And I can act by many vector fields. So I get a map from the symmetric algebra of T times V to V. So this data is equivalent giving such a map and extending it to the symmetric algebra. Okay, so I'm just going to apply the same vector field many times with some functions. Okay, so now what does this mean? So now let's think of this data. So this means an action of functions on T star x module structure on V. We've taken V, which was a module over functions on x, and we've said how to act on it, not just by functions on x, but by functions on T star x, which are polynomials in the tangent bundle. So in other words, we lift V from an OX module to an OT star x module. So in other words, maybe to write it, so this is the same as giving V, have some kind of calligraphic V, which is an OT star x module such that it's pushed forward. Maybe I shouldn't call that pi. What else could I call it? I'm going to call it pi. Sorry. So pi is not, well, it's going to relate to the other pi, hopefully. So now I'm using pi for this. So it's a projection of V is our ordinary V. So you take V and you lift it to a sheaf on the cotangent bundle. You give the action of functions on the cotangent bundle. So this is an equivalent way of saying a Higgs field. It's a geometric way of saying a Higgs field. It's a sheaf on the cotangent bundle, coherent sheaf on the cotangent bundle, which pushes forward to give V. OK, so what can I do with this? Now I have this geometric data. So to such a V, so now I finished with the equivalences. I'm going to now think of a Higgs field as this geometric data. And now what can I do with this? I can assign to it a Riemann surface y, algebraic curve y, which is inside of T star of x, which is the support of V. So if I give you a Higgs bundle, I think of it as a sheaf on the cotangent bundle, and we look at its support. So maybe I can draw what's going on. So we have, here's my x, and here's T star x. And what we've done is we have a sheaf on the total space, and we look at its support. And this is going to be my y. mapping to x. So we have a vector bundle. So what has happened? We look at this vector bundle. This is my vector bundle V. And we've taken these vector spaces, and we've kind of smeared them over the fiber of the cotangent bundle. We've given an action on these vector spaces of functions on these fibers. So that tells me some collection of subspaces. So this vector space is going to be decomposed into a sum of pieces coming from the sheets of Y. So how do I think of this? So the fiber, what's the fiber of this surface Y over a particular point x in x? So let's think about what our translation is. How do we think of this in terms of the original eta? Well, we have a matrix of one forms acting on the fiber. Look at the fiber of V. It has a matrix of one forms. So you can look at its eigenvalues. And its eigenvalues are now one forms. We have just a matrix of one forms. You diagonalize it, or I'll put it in Jordan form, and then you get, so here, this is all sitting inside of the cotangent space. So the fiber of Y, which is a subset of the cotangent space at x to x, these are exactly the eigenvalues of the matrix eta. That's just translation of what we did before. And what is this sheaf V? So V is the corresponding eigenspaces. So every time you pick an eigenvalue at this point, you look at this vector space, and you look at the corresponding eigenspace, some piece here, and you put that piece as a fiber of my sheaf Y. So the sheaf, so the fiber of V at Y is the, I'll call it the Y eigenspace of eta on V at x, which is a push forward of Y. I guess it's just called put image. Okay. All right. So this is the picture. We've assigned a surface, and this surface is just collecting all of the eigenvalues of my matrix of one forms. And for each eigenvalue, you write down the corresponding eigenspace. And you get some kind of sheaf that's supported on a curve inside of the cotangent bundle. And now, what is this curve? Well, what's the equation for Y? So Y is cut out by some equations inside of the cotangent bundle. Well, Y is the eigenvalues. So it's cut out exactly by the characteristic polynomial. So the equation for Y is exactly the characteristic polynomial of my Higgs field. So if I am interested only in this curve Y, all I need to remember from this Higgs field is its characteristic polynomial. And that's going to cut out, that's going to tell me what all the eigenvalues are. And that's going to cut out some curve in the cotangent bundle. OK, so now let's draw this as a picture. So this is, OK, so what does this give me? So I want to use this as a map. So I'm going to think of this as a map, T star bun n of x. So this was the cotangent bundle of bun n of x. But now I'm going to give you a different map. I'm going to say this is the set of pairs of V, and I'm going to think of this as V and V. Or if you like, I just give you this sheaf V on the cotangent bundle. Or if you can think of it as this V and eta. You can think of it either as the sheaf on the cotangent bundle or as just this Higgs field. And what I'm going to assign to this, I'm going to assign to it, I'm going to map to some space B. So this map is called H for Hitchin. This is, what is the map? The map is going to assign the collection of Y's. So, so this is the curves Y inside of T star x, which are n to 1 over x. And the map is you take you take V to its support. Or if you'd like, if you take eta to its characteristic polynomial, and you look at the curve that cuts out. So we map from this cotangent bundle has a nice projection to the space of these curves cut out by characteristic polynomials. Well, what is this Hitchin base space? So, well, B has a nice description. I mean, we can think of it geometrically as a space of curves. But these curves are cut out by specific, very specific equations that are given by the characteristic polynomials of the Higgs field. So I can write this as just the space of characteristic polynomials. So what is of these characteristic polynomials? So what does the characteristic polynomial of an eta look like? Well, we can take, so the characteristic polynomial of eta, so that's what is that? That's determinant of, well, I'm going to get my signs wrong. So I'm just going to say the characteristic polynomial of eta is given by something like some power of a parameter, and then it has the trace of eta to the power t to the n minus 1, and then it has something like the determinant of eta. So where do these things live? The trace of eta is, again, a one form. So eta was a matrix of one forms. Its trace is just a one form. The determinant is a holomorphic n form. So here, where does this live? It has a one form part. That's the trace. It has a quadratic part. That's given by something like the trace of the square. And it goes all the way up to holomorphic n forms. So these are sections of powers of the holomorphic tangent bundle, cotangent bundle. So this is so the point is that the space B is just a vector space. The space of these spectral curves, they're given by these equations in the cotangent bundle. It's just a vector space. It's a direct sum of sections of powers of the cotangent bundle. So we have a map from T star of bun n to B to a vector space. So what properties does this map have? Well, it has very beautiful properties. So the first thing to say, perhaps, is what is its dimension? And this is, so the first claim is that the dimension of B, by a Riemann-Roch calculation, shows that the dimension of B is the same as the dimension of bun n of x, which is half the dimension of the cotangent bundle. So we have a projection onto a base of the same dimension. That's one first calculation to make. Now, let's, inside of B, pick out a part. So I didn't really say what these curves y look like. So if I look at these etas, sometimes they'll have distinct eigenvalues, sometimes they won't. So you would expect that the generic eta will most of the time have distinct eigenvalues. And if it has distinct eigenvalues, the curve y will be a smooth curve inside of the cotangent bundle. In general, this y can be singular, it can be non-reduced, it can have all kinds of problems, but I'm going to ignore them. I'm going to say inside of B, I'm going to look at an open locus, the regular part of B, which is going to be smooth y's. So I'm only going to care about these when these equations define a nice smooth curve. So, and now what is the Hitchin map on such a smooth y? Let's see, what is the inverse of a smooth y? Well, what was the data if given a spectral curve? I think I need another pen. So if you're given a smooth curve, we're going to look at mapping branched n-fold to one. So it's a branch n cover, so it really somehow looks like this picture over x. And what are the possible Higgs bundles that have y's at the support? What is the additional data? What we're missing is the sheaf. And the sheaf is, in the generic case, is going to be just a line bundle on y. This is just pick y. In other words, if you give me, if things are generic enough, then the data of a Higgs bundle is just given by giving the y and given by the sheaf. This is my v. The v is just going to be a line bundle on its support, which is this curve y. So in other words, we have a map where the fibers over some nice, so here this is for y in B reg, the fibers over over a generic point are actually abelian groups. Maybe for distinction, we can ask what's the H inverse of 0. And what do I mean by 0? I mean, I'm thinking of this as a vector space. So I can look at, sometimes I want my characteristic polynomial, maybe my matrix will be nilpotent everywhere. So its characteristic polynomial will be identically 0. And then I get all kinds of crazy things. So what does this look like? Well, in particular, it contains inside of it just the moduli space of rank n bundles itself, thought of as the 0 section. So these are, I'm thinking of these as 0 Higgs fields. So one way I can have 0 characteristic polynomial is if my Higgs field is itself just plain old 0. But it also contains plus other irreducible components. So it turns out that this is, the fiber over 0 is a bunch of components of the same dimension. And this thing is usually called the global nilpotent cone, because it has to do with when eta is nilpotent. OK, so what are some other properties of the Hitchin map? Well, we looked at so let's see, what does this look like? We have a fibration inside of here. We have this nice smooth locus, the fibers over which are these picks of the corresponding curves. So over some nice locus, we have a family basically of abelian varieties, except we have these bad points where the spectral curve gets bad, in particular if you look at this 0 point, and there we have some crazy components. But the generic fibers are as nice as they can be. They're abelian varieties, or times the lattice. So what else can we say about this map? So we notice that the base has the same dimension as Bun n. And in fact, this map H is a Lagrangian fibration. It's a Lagrangian fibration which is generically going to be transversal to the projection on Bun n. So let me just remind you for a second that we already solved this picture in the abelian case. Remember that in the abelian case, we had T star of pick, which was isomorphic to just pick cross a vector space, maps to the Hitchin base, which is, in this case, just this vector space. And the fibers are just the picks, just projection onto a product. So this picture is an exact generalization of that story to the non-abelian case, except that this nice picture only works on an open locus. There's some complicated singular locus where things happen, but this is telling us that we can approximate. So the 0. So here the generic point looks like an abelian variety. The fiber over 0 has some component which is Bun n, and then it has a bunch of other irreducible components. So we have a kind of picture like this. We have a fibration where most of the fibers look like abelian varieties, and then some fibers look crazy. But it's a way of thinking of this moduli space Bun n that it's very nicely approximated by a family of something as nice as you want, namely Picard groups. OK, so this is the abelian story. And this shares a lot of other features with the abelian story. For example, the map is proper on each component. So maybe I'll write that on a separate board. So the same kind of statements that we had in the abelian case generalize. So if you want to look at functions, suppose I wanted to describe functions on T star Bun n. So functions on T star Bun n, and I'm really going to restrict to some connected components. But all the functions on T star Bun n come from the base. So we have a map from this T star Bun n to a vector space. So there's lots of polynomial functions on this vector space. You can pull them back, and you get a bunch of functions on here. And the claim is that these are all the functions. So you've actually described all the functions. So in some sense, it's, again, like the Jacobian case, where the fibers were proper. Fibers are these abelian varieties, so there are no functions along the fibers. All the functions come from the base. And these functions, these all Poisson commute. So I don't want to get into the symplectic geometry of this too much, but these functions all Poisson commute, and they define a completely integrable system, which is Hitchin's. This is Hitchin system. It defines a Hitchin integrable system. So for our purposes, this integrable system will just be a Lagrangian projection, a Lagrangian fibration. Okay. Are there questions about this story? Okay, so this is our picture of Bun N. That at least the cotangent bundle of Bun N can all be described in terms of these abelianized story. So maybe I should just repeat this again. This is saying that if you have that the data of a Higgs field, at least generically, it's the same as the data of an abelianization. It's the same as the data of saying, write your vector bundle as the push forward of a line bundle from some cover. Except that these covers are all sitting inside of the cotangent bundle. So it's very special kind of covers. But that's what this, so this is how to think of T star Bun N. It's the data of vector bundles plus abelianizations. Okay, so maybe I should quickly say that everything works the same for any reductive group. So let me maybe just the outline. So you can't quite say it as easily. You have to come up with some terminology. But let me just draw the picture again that T star of Bun G of X, you can think of a Higgs field on any G bundle as an abelianization data. It's defining some kind of abelianization. It defines a map onto a base B. So there's a map onto Bun G, and there's a map onto a base B, which is, in this case, again, it's again a vector space, and it's a sum over a bunch of powers of sections of the. So it's a sum over, these are the exponents of my Lie algebra. So main point is it's a sum of various sections of powers of the cotangent bundle. There's again, and what does the, so maybe I'll draw the picture, and what does the fibration look like? So again, it shares all the properties that I wrote. All the functions come from the base. They all Poisson commute. The fibers are all Lagrangian. What else do we have? And what is the generic fiber? And the generic fibers are, again, abelian varieties. So let me draw that, try to draw a picture of this. So I have base space B. Inside of it, I have some discriminant type locus where my characteristic polynomial is not regular. So there's a discriminant locus, the complement of which, so this is going to be my B reg. And I have my space T star of Bun G maps down to this vector space. And the fibers away from the discriminant locus, they let me give it also a notation. If I look at T star Bun G mapping to B on B reg, the fiber, I'll call it A, is a family of abelian varieties. So A is it's a family of abelian varieties, at least roughly. So there are things that look like abelian varieties. They might not really have a base point. You might not be able to choose a canonical base point in a nice way. These are not Picard groups anymore, but they're what's called prim varieties. So they're really things like cosets inside of components of abelian varieties. But at least to first order, what you have here is you have a fibration by these abelian varieties. And of course, I guess even in the PIC is not quite an abelian variety. There's also some lattice, some component group. And then over the point 0, for example, which is the worst point, we have a component which I don't even have a good idea how to draw, which is Bun G itself is an irreducible component of the 0 fiber. So there's a very complicated zero fiber, but the generic fibers look like these abelian varieties, or like more precisely these prim varieties. Okay. Wow. Okay, so what can we do with this? Well, this is exactly the kind of picture we started talking about before. You have a family of abelian varieties over a base. You can do a Fourier-Mukai transform. So what I'd like to do is look at, this is a family of abelian varieties over some piece of this vector space. So over this piece, I can look at the dual family of abelian varieties. So these are fiber-wise characters, or degree 0 line bundles on A. So on each, I'm going to just look at these characters on each fiber of this fibration, away from the locus I don't understand. And so what do these things look like? Well, in the case of GLN, we said A was just a bunch of Picards. So it was basically a bunch of Jacobians of Riemann surface. So A is basically Jacobians of Riemann surfaces. So I'm going to ignore the components. So it equals A dual. The Jacobian was self-dual. So in the case of GLN, this picture is self-dual. So we have some open piece on which we have a self-dual fibration. So how do we? So that in particular, this tells us for GLN, we get a kind of Fourier-Mukai statement that for GLN, the derived category of A, O, has some funky auto-equivalence. Well, in general, we're going to have such an equivalence. But in the case of GLN, this is going to be A again. So we're just going to do the same Fourier-Mukai transform on each fiber. So what does this, how does this generalize to other groups? So now what's the kind of real picture? And this is where the geometric Langlands correspondence comes from. So I'd like to try to get to state the geometric Langlands conjecture. It's motivated by this picture. So again, let me say we're trying to study some kind of categories of sheaves on Bun-G or T-star Bun-G, and we're trying to understand, is there some kind of nice Fourier story? And now we've realized that if you look not on Bun-G but on T-star Bun-G, it looks like a family of abelian varieties over a vector space, at least away from some singular fibers. So there's a natural Fourier transform to do. There's a nice Fourier duality. And in the case of GLN, these abelian varieties were just Jacobians. So we found that there's some self-duality in GLN. So the way I want to state that there's a theorem. So this theorem historically was motivated by geometric Langlands, but I'd like to sort of reverse the order. So this is a theorem of Ron Donaghy and Tony Pantev, which has kind of a long history. This is in the GLN case, this was done by Thomas Hausel and Michael Thaddeus. And similar pictures appeared in the physics literature before. But the theorem that I'm going to state is due to Donaghy and Pantev. And it says that, well, let me just draw the theorem as a picture first, and then I'll state it. So we look at T-star Bun-G. It maps to this Hitch and base space. And I'm going to draw things this way. We look at this regular locus of the Hitch and base space, over which we have this abelian fibration. Now I'm going to look at the dual fibration. And the theorem says that this dual fibration naturally sits inside of T star of Bun-G dual. So we have the same Riemann surface. We're looking at the cotangent bundle now of Bun-G dual, where G dual is another group that I'm going to introduce. It's called the Langlands dual group. And in fact, it's a Langlands dual group whose Hitch and base is identified canonically with the same Hitch and base. So there's another group that's coming out here kind of out of nowhere, whose Hitchin system lives over the same base and has the same regular locus. And over the regular locus, these are just dual abelian fibrations. And the theorem then says that we have an equivalence of derived categories. Well, dAO is equivalent to dA check O. So this theorem is essentially some fancy version of Fourier Mukai. I've been a little misleading about what exactly these fibers are. The fibers are a little more complicated than I've been letting on. They have words like gerbs and such in front of them, but they essentially look like abelian varieties, and this is essentially a Fourier transform. For groups other than GLN, you have to be a little more subtle. But let me just say it this way. So what does this fibration look like? So of course, this would lead you to conjecture. This is maybe called the classical geometric Langlands. We'll see the meaning of the word classical in a moment. That the same thing holds for the full spaces, T star bun G. This Fourier Mukai extends to the full cotangent bundle of these two spaces. On an open set, it's just a Fourier transform along this Hitchin system. But you might conjecture that it extends to a Fourier transform on the full space.
Is there a uniqueness statement?
Yes. So I haven't said very much about where right now this has come kind of out of the blue. We just noticed that the Hitchin gives us an abelianization. It gives us a way of thinking of these G bundles as being very close to line bundles. And we know how to do with line bundles. And so this says that the moduli space, T star of bun G, looks a lot like the abelian story. So we can imitate it. Now you might ask where this comes from, and what's the uniqueness, what are the special properties, and all of that will be discussed tomorrow. But for now, this is no. I think the strongest theorem in this direction is the Donaghy-Pantev one, but it's on this open locus. Everything is on this open. And when I said these conjecture, and when I'll say the geometric Langlands conjecture, it should be taken a little bit with a grain of salt. I mean, I don't know if it's. I don't believe this is literally going to be the case. It's going to be you have to think of the two sides in a slightly DG, whatever. You have to sort of mess with the two sides in slight ways that I don't really understand. And I don't think it's been stated in a complete version that everyone really believes. So but something that's roughly like this is expected to be true.
Suppose we set n equals to 1.
For n equals to 1, in fact, we discussed this. And this was exactly T star of the Jacobian, which was self-dual. So the GL1 is its own dual group. I'm going to discuss what the Langlands dual group, that's going to be basically the topic of tomorrow, what this Langlands dual group is. I guess I should just say, for now, let me just say that GLN dual is GLN. That doesn't tell you much what it is. But generally, it's going to be a reductive group of the same rank with a dual. So G check is a reductive group with dual torus and root data. So it has a dual maximal torus, and it has the dual root data. And I'll explain tomorrow what I mean by this and why this might come up. But for now, it's just there's another group out there. For GLN, it happens to be the same, which is why we got a self-duality. And
these are always complex Lie groups?
Yeah,
Yeah.
always.
We are staying completely
Complex reductive algebraic groups.
in the world of complex
Yeah.
reductive Lie groups.
Yes. And so this is the conjecture. And so let me just point out some features of this map that what I want to explain is that all of the picture that we drew for the Jacobian, you might expect to extend to this. All the kind of features we had in the case of the Jacobian, you might hope to extend to this setting. So now let me write down the geometric Langlands conjecture in a form of the geometric Langlands conjecture. So the geometric Langlands conjecture is saying that this picture, this was not what we were actually interested in the case of the Jacobians. we were interested in D modules. We were interested in flat connections on the Jacobian. This was kind of the degenerate version. We then deformed this. And what we did, we deformed the two sides in different ways. One side got deformed in a non-commutative way. Another side got deformed in an affine way, in the case of the Jacobian. So now we're going to say the same thing. And again, this will become much more better motivated tomorrow. But at this point, you could just say, let's take the two sides. I'm going to take the left-hand side and deform it. Instead of looking at the cotangent bundle G O modules on the cotangent bundle, I'm going to look at D modules on bund G itself. That's a non-commutative deformation of this. And the equivalence says that this should go to, well, this should be deformed now in an affine bundle, like we saw in the affine case. Which affine bundle? There's a natural one that's already appeared, the space of connections, G dual local systems, G dual connections, and we just look at O modules on that space. So if you remember, this is exactly what we had in the case of GL1. This was exactly the Fourier transform we had in the case of GL1. The claim is that this should deform, this equivalence should deform to an equivalence like this. So it's a kind of a Fourier transform for D modules on bund G. Unfortunately, you no longer have this abelianization picture. It kind of goes away when you quantize. It kind of fizzes away. And of course, this conjecture is going to be a lot more pinned down. We don't want just any old equivalence. This equivalence is going to have various properties. For example, it should take skyscrapers here to special things, which we're going to call eigensheaves. So I mean, and that are going to have nice characterization properties. But maybe I should just conclude with telling you a little bit about what's known. Let me just draw again this dual Hitchin systems. So I have these dual Hitchin systems. So I'm going to ignore the bad fibers, because I don't have any idea what happens there. But away from the bad fibers, we have these abelian varieties. And these are dual abelian varieties. So what do we know about these dual abelian varieties is, so if I take the origin of these abelian varieties, a skyscraper at this point should correspond to the structure sheaf of a fiber. So skyscrapers in the skyscraper at the origin of one of these, of a Hitchin fiber, H inverse of H check inverse of y. So I have a point y. I look at its fiber. It's an abelian variety. And the structure sheaf at 0, we decided the skyscraper at this point should correspond under the Fourier-Mukai transform to the structure sheaf O of the fiber of H inverse of y. Structure sheaf of this fiber on this side. So a point here corresponds to the trivial line bundle, to the structure sheaf of one of the fibers. So in order to make that precise, I first need to say that there is actually a section. So Hitchin constructed also a section of this map. So in the abelian case, we could look at the space of the fiber. Yeah, so in the abelian case, we looked at the fiber over the trivial bundle. We had the notion of the fiber of the cotangent bundle over the trivial bundle. And that's somehow not the right space to look at. But what I want to say is that Hitchin defined a section. There's a section. So there's the map B to this T star bun G check. And Hitchin defined a nice section. And the points on this section exactly correspond to structure sheaves of fibers on the other side. So that's, again, the same kind of story we had in the abelian case. So now what I'd like to conclude with telling you, just giving maybe a very impressionistic picture of maybe one of the stronger statements that's known in the non-commutative case. So let me just remind you that in the abelian case, we saw that this particular slice we could deform. So in the abelian case, we looked at the space of connections on GL1 connections on X, and inside of here we had connections on the trivial bundle. And if you look at connections on the trivial bundle, we knew what to assign to them on the other side. So this was this slice, this kind of deformed slice of the Hitchin fibration. This sits inside of this space Jack. It was a particular fiber of the projection from Jack natural to. So this is my caricature for Jack natural. This is the caricature for the Jacobian. And there was a particular slice in here, which is connections on the trivial bundle. And we knew how to assign. There was a very concrete way to take a O module here and assign to it a D module on the Jacobian. So O modules on this connections on the trivial bundle, we assigned to it particular D modules on the Jacobian by identifying, this came from the fact that functions on the base were identified with global differential operators on the Jacobian. So you look at these functions on the base, you identify them with global differential operators on the Jacobian that enable you to explicitly take connections on the trivial bundle is isomorphic to this base that enable to explicitly write down a connection on the Jacobian. So, right, so maybe this is very impressionistic at this point. I just want to say that all of this picture has been done in the non-abelian case. And this is the theorem of Behlens and Drinfeld. Behlens and Drinfeld, they've constructed this geometric Langlands transform. So let me call it, I don't know, call it F of this Fourier transform. So they construct this desired geometric Langlands transform on a particular fiber of the space of connections G check over Bund G check X. So we don't know what to do with arbitrary connections, but we know what to do with very special connections, which this fiber is isomorphic to the Hitchin base B. So there's a particular fiber in here that's just like in the abelian case is isomorphic to the Hitchin base, and the construction comes from exactly the same argument because they show that they identify functions on the Hitchin base with global differential operators on Bund G up to some little twist, which I'll ignore. So the same picture that we saw in the abelian case can be done. The explicit part of the Fourier Mukai, where you can really explicitly write down these D modules as by quotients of D by explicitly defined global operators. You identify the globally defined differential operators up to some spin structure. There's some little prime, which I'm ignoring. You identify these global differential operators with functions on the Hitchin base, which are the same as functions on this slice on this particular fiber. And this fiber, I believe, will appear in Konstantin's talk, so I should give it a name. This fiber is called OP G check. It's the moduli space of G check opers. So it's a particular kind of connections, which they call opers. And they are able to imitate all this, well, which is much, much harder than the caricature we had before. But so this is one of the stronger pieces of evidence for the geometric Langlands conjecture. I should also mention that this conjecture is also known for GLN on an open locus, of irreducible local systems. So maybe I'll write that down. This is also known in the case of GLN on the locus of irreducible connections. And this is due to work of Frenkel, Gatesbury, and Villonen. OK, so tomorrow we're going to leave this behind, and I'm going to start from scratch from a different point of view to motivate why this conjecture, where does this conjecture come from? where does the dual group come from, and what is the dual group?